Solubility equilibrium. We looked at, or you looked at, solubility rules in Chapter 4 back in Chem 1A. We learned to look at these rules and say, oh, this compound is soluble, this compound is insoluble. And that was it. But actually there are degrees of solubility, and now we have the tools to look at that. So an ionic compound dissolving is an equilibrium. And what is wrong with my chemical equation? Anybody see it? The reactant should be a solid. That's better. How can we dissolve something that's aqueous already? That doesn't work. Okay, we have calcium fluoride, solid, and as it dissolves, it forms calcium ions and 2 fluoride ions. These are aqueous. This is a solid. This is an equilibrium. And so we can write an equilibrium constant for it. It's the products multiplied and raised to a power equal to their coefficient, and it's divided by the reactant. But the reactant is a solid. Remember, we leave solids and liquids out of equilibrium constants because they can't change their concentration. So what we have is the calcium ion concentration times the fluoride ion concentration squared. That's the equilibrium expression. Well, we're going to call it KSP. Now, we've had Ka and Kb, and we had Kc and Kp as well, and now we've got KSP, right? The SP, solubility product constant. It's the solubility product. It's the product, the multiplication of those 2 ions that are formed. It's a measure of the solubility of a compound. If KSP is high, more of the solid will dissolve. If KSP is very small, very little of it will dissolve. So let's look at silver chloride. I think I missed something. Yes, I did. Okay, molar solubility. When we talk about solubility, what we mean is the quantity of the compound that dissolves in a certain amount of liquid. And in Chapter 4, they often talked about, I think it was grams of solid per 100 grams of water. And that's a common unit for measuring solubility. We're going to talk about molar solubility. Molar solubility is just the solubility in units of moles per liter. So we're going to look at how many moles of this would dissolve in a liter of liquid. We can calculate this from the KSP, but it's important to remember that KSP is not the molar solubility. They're related, but it's not the same. KSP has one value at a given temperature. You change the temperature and the KSP might change, but regardless of what's going on in the solution, KSP at a given temperature is a constant. The solubility, the molar solubility, can vary in different solutions. And we'll see one of the things that can affect molar solubility is the common ion effect. So to find the molar solubility, we're just going to do an equilibrium calculation. Now we get to this slide. So let's look at silver chloride. There's the KSP, the solubility product constant. What is the molar solubility of silver chloride? Well, we think of this initial, there being no silver ion and no chloride ion in the solution. The change will be plus S and plus S. Remember, we're leaving this guy out because he's a solid. And it doesn't really matter how much of him is there as long as there's some there. The concentration won't change. They're using S here. You can use X. I was scribbling on paper at home and I realized, S looks an awful lot like a 5 sometimes. So I'm going to use X's instead of S's. But they use S because S is solubility. So I'm going to call this X and this X. And then this is X and X. So what we come down to then is the KSP is 1.77 times 10 to the minus 10, and that's going to equal X squared, right? So in this example, the solubility is just the square root of the KSP. So molar solubility for this guy equals 1.33 times 10 to the minus fifth moles per liter. That's pretty low. From the solubility rules, we said that silver chloride was not soluble. And it is not appreciably soluble. This is a very small concentration. Any questions? Here's a table of solubility product constants for some different compounds. When you're doing mastering chemistry homework, you'll come up with a better result if you use the values from the book. I know you can Google them, and sometimes that's faster, but they can vary a little bit depending on who's reporting them. Let's calculate the molar solubility of iron 2 hydroxide in pure water, and I copied the KSP down there for us. So what do? Ice table. So we've got, let's just draw do the whole equation here. We've got FeOH2, and that is dissolving to form Fe2 plus and 2 OH minus. The 2 is important there. So I can just make my ice table under my equation here. Initially, we've got 0 and 0. What's the change for the iron? We'll call that plus X. What's the change for the hydroxide? Plus 2X. Ooh. So here we've got X, and we've got 2X. KSP, which is 4.87 times 10 to the minus 17 equals X times 2X, the quantity squared. It's important to square the quantity because the 2 gets squared as well. So that is 4x cubed, right? So that is the, wait, that's not what I wanted to do. It's the cube root of 4.87 times 10 to the minus 17 divided by 4. Pardon me? Never mind. Yeah, this is what I'm doing on my calculator. The cube root of 4.87 times 10 to the minus 17th divided by 4. The 4 gets in the cube root. It doesn't always. Yeah, it doesn't always come out right when you say it. So x ends up being 2.3 times 10 to the minus 6. Any questions? It's so easy to make calculator mistakes. It's really, really easy. And that's why it's a good idea to write down what you're doing and look at it and go through it again. And, you're doing mastering chemistry, doing examples in the book, and you look and you see, oh, that's not the right answer. Well, go back and look for some math mistakes first. That's probably what happened. We can also calculate KSP from the molar solubility. So the molar solubility of silver bromide in pure water is 7.3 times 10 to the minus 7. What's KSP? So let's think about this, but first I need to select the marker tool. So let's think about what's going on. We've got silver bromide dissolving to form silver ions and bromide ions. This molar solubility tells us what? It tells us the concentration of silver ion and bromide ion, right? Because if I have 7.3 times 10 to the minus 7 moles of this that dissolve in 1 liter of solution, these are the concentrations I'll get, right? Now, if it was PbBr2, then you have to be careful, huh?
Yeah.
You got to be careful. So watch out for that. I'm sure there's probably one like that in the homework. KSP equals, so it's going to be 7.3 times 10 to the minus 7 squared. Oops. 7.3 times 10 to the minus 7 squared. 5.3 times 10 to the minus 13. Any questions? So we just saw that you can calculate the molar solubility from the KSP, and you can calculate the KSP from the molar solubility, so they are related. But you cannot always use KSP values to compare the relative solubilities of two compounds. Let's look at these two, magnesium hydroxide and iron 2 carbonate. If we look at KSP values, which one is more soluble? The iron carbonate, right? Because it has the larger KSP. But if we look at molar solubility, which one's more soluble? The magnesium hydroxide.
Is that because you have two hydroxides? It has to do with...
Yes, it's because of the stoichiometry. Because this is MgOH2. And so that figures into the KSP. It makes it look very different. So the relationship between the KSP and the molar solubility depends on stoichiometry. If you're comparing two that have the same stoichiometry, then the KSP, relative KSPs will reflect the relative solubilities. Here, the CaF2, calcium fluoride, is more soluble. It has a larger KSP, and the solubility, molar solubility, is higher. So you can only compare apples to apples. You can't compare apples to oranges. So that's, just watch out for that. I mentioned earlier that KSP has one value at a given temperature, but the solubility, the molar solubility, can vary depending on the solution that it's in. So in general, the solubility of an ionic compound is lower in a solution containing a common ion than in pure water. So if we look at calcium fluoride dissolves into calcium ion and fluoride ion. If we're doing this in a solution that contains fluoride ion from some other source, what does that do to this equilibrium? It shifts it to the left. What does that do to the molar solubility? It makes it go down. The common ion makes it less soluble.
Make it precipitate?
Not as well. We'll talk about that.
So if you have like multiple compounds but none of them have common ions, would they be like it doesn't affect each other at all?
What if you had multiple ionic compounds but no common ions?
Well, like so you have like a liter of water, you have a bunch of like calcium and fluoride dissolved in it, but then you have a bunch of like
if you have different ions that do not interact, forming insoluble compounds, it doesn't matter.
At all.
No, it's just the common ion.
Okay.
Okay. Any other questions?
Yeah, that was my question from the homework. It was like the last one was like this in this type of solution, but there was no common ion.
There's one tricky thing is pH. If the anion in your solution is the conjugate base of a weak acid, then the solubility will be pH dependent. And so you have to watch out for that. Calculate the molar solubility of calcium fluoride in a solution containing 0.250 molar calcium nitrate. So let's write out the equation so we can see what's going on. It always helps me to write the equation, helps me to organize my ice table. So we've got calcium ion and we've got 2 fluoride ions. So initial Well, normally the initial concentration would be 0, right? But can we say that the initial concentration of calcium ion is 0? No, there's 0.250 molar of it from the calcium nitrate. Calcium nitrate is very soluble. Nitrate compounds are very soluble. So we don't have to worry about KSP for that. That's going to completely dissolve. We're going to say that the initial concentration of fluoride is 0. So that's our initial. And then change. Which direction is this going to go in? Can it go to the left? Can we lose fluoride ion? No. It's going to go to the right, but it's probably not going to go very far. If you said to yourself, well, it's going to go to the left, what you'd end up with is a negative x, and it would fix itself in the end. This is going to go plus x, and this is going to be plus 2x. So at equilibrium, we're going to have 0.250 plus x, and we're going to have 2x. So now we use KSP. The KSP was given 1.46 times 10 to the minus 10. That equals 0.250 plus x times 2x, the quantity squared. Do you think x is small? Yeah, probably. This solubility product constant is very small. That tells us it's going to go this way, a very small amount, and this initial 0.25 is fairly large. So we'll go with the x is small, and when we do that, we just ignore this guy. So now I'll write this out, but not with the highlighter because that doesn't work very well. X is going to equal the square root of 1.46 times 10 to the minus 10 divided by that 0.25 and divided by what? 4. Because that 2 got squared. I'm coming up with x, no, that is x. X equals 1.21 times 10 to the minus 5. So that's the molar solubility of calcium fluoride in this solution that already has calcium ion in it. The calcium ion causes the equilibrium to shift and causes the calcium fluoride to be less soluble. Any questions? Pardon me? Indeed? Good. Effective pH on solubility. So the pH of the solution can affect the solubility of a compound. Let's look at magnesium hydroxide. This is the active ingredient in milk of magnesia. Have you ever wondered how is it that we can swallow bases when we have acid indigestion, heartburn, and it doesn't just dissolve our esophagus? How does that work, right? Because if you swallowed sodium hydroxide, you'd be in a world of hurt, right? That's not a good idea. So how can we eat magnesium hydroxide and not damage our tissue? Well, it has to do with the pH. At high pHs, the common ion effect is going to decrease the solubility of this compound. Magnesium hydroxide, that is one of those metal hydroxides that's not very soluble. If we have a high pH, we have more hydroxide, a common ion, and that's going to cause the magnesium hydroxide to be less soluble. At low pH, there's more acid present. Where is the magnesium hydroxide in milk of magnesia going to encounter an acidic environment? In your stomach, right? So here there's acid in your stomach. It's going to react with the sodium hydroxide, causing this concentration. It's going to chew up the sodium hydroxide as it's released. And so that will cause the equilibrium to shift. And that's how you can swallow magnesium hydroxide and have it reduce the acid in your stomach without destroying your esophagus on the way down. So in general, the solubility of an ionic compound with a strongly basic or weakly basic anion is going to increase with increasing acidity. So the more acid it is, the solution is, the more soluble it is. The common basic anions are hydroxide, of course, but also sulfide and carbonate. Hydrogen sulfide is weak acid. Hydrosulfuric acid, carbonic acid, a weak acid. So this concept is actually created, well, it's not really the concept is created, but this is the chemistry behind the formation of a lot of caves. If you have a rock that has a high limestone composition, limestone is calcium carbonate. Rainwater is naturally slightly acidic because it's got dissolved carbon dioxide in it. Right? The rain is falling through the air, which has a lot of carbon dioxide in it. Yes, question?
So it's, there's been a big deal about acid rain.
Well, acid rain is bad. It is. But rainwater is naturally acidic. It's just that the acid rain is too acidic. So the rainwater washes through the ground and comes in contact with the limestone, and calcium carbonate is not very soluble, but it's more soluble in an acidic solution. And so it will dissolve the limestone. It can create these really amazing caverns. And then as that water drips, that's saturated in the calcium carbonate, that's what's forming the stalagmites and stalactites in the cave. So you've got the saturated calcium carbonate solution, and it falls on the ground, and then as the water evaporates, the calcium carbonate gets left behind. So chemistry is chemistry. Which compound, iron carbonate or lead bromide, lead-3 bromide, is more soluble in acid than in base? I think there's a typo in there, but I don't think it really matters. And why? So, more soluble in acid. What sorts of compounds would be more soluble in acid? Those that have a weakly basic anion, right? Well, carbonate. Carbonate is the conjugate base of which acid? Carbonic acid. And bromide. Bromide is the conjugate base of what acid? Hydrobromic acid. Is hydrobromic acid a strong acid or a weak acid? It's a strong acid. This is a strong acid. And so then bromide does not function as a weak base. It just really doesn't function as a base at all. But this is a weak acid, and so the carbonate ion functions as a weak base. So it's this one.